All right. So I decided to call my project Exploring Methodology for Quantifying Snow Avalanche Disturbances, a case study. So snow avalanches are one of the most common forms of mass wasting in the Rocky Mountains. And they're a fundamental force in shaping the plant and animal communities in the alpine and subalpine ecosystems. They're also more frequent than other disturbances in these ecosystems, and they usually occur about once per season. Avalanches form paths in the landscape that are free of trees and large shrubs. So this image on the right shows is a really good example of how avalanche paths shape the landscape. I took this photo this summer from Huron Peak down near Aspen. Avalanches vary in size and destructive potential, and they occasionally run much larger than the path that already exists. In the past, dendrochronology has been used to determine the return interval of large avalanches by finding the ages of trees that are felled by the slide, since those trees essentially grew to be that old before an avalanche large enough to destroy them did destroy them. However, these methods of dendrochronology are very labor intensive and are sometimes limited by access to terrain. So the goal for this project was to explore other methodology to determine the change in vegetation and return interval of large avalanches using remote sensing of aerial imagery and statistical analysis of changes in snow water equivalent, which I will refer to as SWE throughout this presentation. So my research questions were, how do large avalanches change plant community composition in alpine and subalpine ecosystems? And are bulk snow accumulation metrics good predictors of the return interval of large avalanches? So I'll start with some background on avalanches themselves and the specific avalanche cycle that I studied. So there's two measures of the size of an avalanche: the destructive force, which is measured on the D scale, and the size relative to the path, which is measured on the R scale. The D scale measures the destructive capability of an avalanche. For example, a D1 avalanche is unlikely to bury a person, whereas a D3 avalanche can destroy small buildings, and a D5 avalanche will uproot trees, gouge the landscape, and can destroy an entire village. The R scale measures the size of the avalanche relative to the existing path. An R1 avalanche is much smaller than the existing path, and an R5 avalanche runs much larger than the extent of the existing path. So there's also three main sections of an avalanche path. In this photo on the left, we have the starting zone in blue, the track which runs vertically downhill, and the deposition zone or the debris field in red. And avalanche paths are defined laterally by their flanks. There's also many different types of avalanches and several factors that determine their size and destructive potential. Dry slab avalanches will be the primary focus of this case study. A dry slab avalanche has three components: the bed surface, which the avalanche runs along, the slab, and the weak layer. A weak layer is essentially a layer of uncohesive snow within the snowpack. Slab avalanches occur when a slab, or a layer of harder snow, slides off the underlying weak layer, kind of like a book rolling over marbles, like on a tilted surface. So weak layers are formed by various weather conditions. One of the most common types of weak layers in Colorado is buried deep in the snowpack and is formed early in the season. It is made up of facets or angular snow crystals that form as a result of temperature gradients within the snowpack. So in the winter of 2019, what some are referring to as a historic avalanche cycle occurred. It kind of all started back in October when snow began to accumulate and facets formed near the ground, forming a persistent slab. On February 28th of 2019, the avalanche danger was rated as moderate by the Colorado Avalanche Information Center. And the problem was a persistent slab. This problem exists throughout much of the season in Colorado's continental snowpack and is the result of those facets near the ground usually. So in early March, a severe winter storm began and it lasted for 2 weeks. Some areas saw up to 170 millimeters of SWE fall during this storm. Prior to this storm, the snowpack was relatively stable, which essentially prolonged the period of snow accumulation before large natural avalanches began to happen. Eventually, the new load of weight on the snowpack caused the weak layers to fail, producing more than 1,000 avalanches, 87 of which were D4 or larger, and this all happened in just 2 weeks in Colorado. Some of these avalanches were larger than had been observed in decades, and new avalanche paths were cut into the landscape all over Colorado. These avalanches destroyed several homes, buried roads, rampaged through forests, and claimed the lives of 3 people. The Colorado Avalanche Information Center rated the avalanche danger as extreme for several days. So to kind of quantify the return interval and the impact on vegetation that these avalanches had, I had 2 main sections of methodology that I used. But first I had to select study sites that I wanted to look at. So what I did was I obtained all the documented avalanches that occurred in March 2019 in Colorado from the Colorado Avalanche Information Center. And then I sorted all of that data to identify the largest avalanches that happened. The result were 2 avalanches, both of which were D5, R5, and these were the 2 largest that happened during this cycle. I then visited these 2 avalanche paths in early October to make qualitative observations of the paths. So moving on to the remote sensing section, my goal here was to explore methodology for measuring vegetation change remotely in order to estimate changes to the plant community composition as a result of avalanches. So to measure the change in vegetation after the avalanches, I first downloaded aerial imagery of the study sites from the USDA's National Agricultural Imagery Program, or NAEP. NAEP provides a 1-meter resolution orthorectified product that is captured during the agricultural growing season in 2-year intervals and has 4 spectral bands: red, blue, green, and near infrared. I downloaded NAEP imagery for 2013, 15, 17, and 19. The 2019 images captured the aftermath of the March 2019 avalanches. The 2015 and 2019 images were primarily used for comparison because the 2013 and 2017 images were taken when there was snow on the ground, which affected later processing. The raster images for each site were mosaicked using ArcGIS Pro. I then digitized a polygon surrounding the avalanche path and then clipped the raster to the polygon. I then used the normalized difference vegetation index raster function to measure greenness and relative biomass at each of the study sites for each year. Next, I used the binary thresholding raster function to apply it to the NDVI in order to classify the raster data into 2 distinct classes. The 2 classes were bare ground, soil and rock, and vegetation. I then used the raster to polygon tool for each of the binary threshold rasters to quantify the area of the 2 classes for each year at each study site. As I mentioned before, the 2015 and 2019 images were primarily used for analysis beyond this point. So then the other part of this project was statistical analysis of snow accumulation. So my goal here was to quantify the frequency of these R5, D5 avalanches in order to determine their return interval based on similar increases in snow water equivalent. To do this, I obtained all snow water equivalent data on record from 4 SNOTEL stations that surrounded the study sites. I then found the maximum change in SWE in 14-day periods. I used 14-day periods because that was the duration of the snow accumulation event that occurred in March 2019. I found the annual maximum change in SWE in 14-day periods for each station, and then I for each station, the mean standard deviation, K value, and return interval was calculated. This would tell me how often similar bulk snow accumulation events occur. So this is a map I made of the study sites and also the SNOTEL stations that I chose. So the study sites were located near Aspen in Pitkin County, and they were relatively close to each other, which does make sense because they probably had very similar snowpack conditions and experienced similar snowfall events. So these are the 4 SNOTEL stations that I chose, and those were the 4 closest to the avalanche paths. So this is an image of the Conundrum Creek avalanche just after it happened. It's pretty impressive. You can see where the avalanche ran down the track and then transitioned to the deposition zone, which is all of here. And right at this transition right here is where Conundrum Creek flows. So the avalanche completely buried Conundrum Creek. And then all of this just kind of like speckled snow is all debris of trees and rocks and soil that had been kind of carried down the avalanche path. So these are images from when I visited this site. Like I was mentioning in the picture before, the avalanche completely filled in the little ravine where Conundrum Creek flows. And this right here is actually a bridge that was left over from the snow that filled in that ravine. So although you can't really see it, this little bridge over the creek is made of snow and ice. And it's supporting all of this weight of logs and debris. And it's also, we probably should have put a person in here for perspective, but these are full-size trees on the ground, so it's really impressive that this snow bridge still stands. It was actually really cool to kind of discover that. We had no idea it was going to be there. Also, this debris field is right along the trail to Conundrum Hot Springs. So this right here is actually the Conundrum Hot Springs Trail. And after the avalanche, trail crews had come through to kind of clear the way so that the trail could still be walkable. But they essentially kind of cut a cross section in the avalanche path. So when we were walking along the trail through the debris field, we noticed that the cross section kind of revealed that there was still snow and ice buried underneath all of this debris. So that snow and ice had lasted 2 summers, and it'll probably be there again next summer since we visited only in October, and as you can see, it was kind of rainy and cold at that time. So this is an image from Cake of the crown of the East Snowmass Creek avalanche. And here are some images from when I visited that site. Conveniently, there was trails that went to both of these sites. So this path, we noticed that there was a lot, like the trees weren't quite as destroyed as in the Conundrum path. And there was not as much like soil and rock in this debris field. The trees were more whole and they kind of looked like they had been tipped over and only carried a short distance rather than like tumbled down the entire avalanche path. So East Snowmass Creek again flows underneath here. We didn't see any evidence of leftover snow or ice this time, but we did see this massive tree, which is right here in the right photo. And there was really great evidence of flagging, which is usually an indicator of avalanches, like persistent avalanches. And its flagging occurs when avalanches knock or prevent the uphill side of the tree's branches from growing. So this example of flagging, you can see there's no branches on this like left-hand side of the tree. And this is a 6 foot tall human right here, just for comparison. The flagging is about 3 times his body height. So this tree's probably withstood a lot of avalanches, and I'm quite impressed that it still stands, but it was pretty ginormous. So that was really neat. Okay, so the results of the remote sensing methods that I used showed that there was an 18% decrease in vegetation at the Conundrum Creek avalanche path, and only a 2% decrease in vegetation at the Snowmass Creek avalanche path. So the detected change was definitely greatest at the Conundrum path, which pretty much matched up with the observations I made when I visited the sites. Here are the images of the Conundrum Creek avalanche path. On the left-hand side are the 2015 images, and the 2019 images are on the right side. So you'll notice the debris field is down here on the right. Those are where the pictures I showed you came from. And Conundrum Creek, you can see in the 2015 images, flows just right along there. So in the 2019 NAPE imagery, you can definitely see the landscape is kind of gouged along the flanks of the path, and a bit down on the lower side too. Now this is the result of the binary threshold that I used on the NVVI output. So you can also see that the changes that are most obvious in the nape imagery are also very obvious in this binary threshold image. So again, here you can see the kind of like gouging of the landscape along the flanks and definitely the debris field. And then another little bit of evidence down here. Here is the same thing for the Snowmass Creek avalanche path. And so the debris field where I took photos was up here in the upper right corner, and then Snowmass Creek again runs right underneath it. This is not, it's pretty clear that there's not as much destruction here as there was at the Conundrum Path. Most of the evidence that you see is right here, but it's not quite as widespread as at the Conundrum Path. There's also another little flank right here. Okay, so the return intervals that I calculated based on 14-day changes in snow water equivalent ranged from 9.8 to 14.3 years and averaged, 9.8 to 39.5 years and averaged 21 years. The Nivio graph of the 2019 water year clearly shows this increase in snow water equivalent that occurred in the first 2 weeks of March. Schofield Pass actually reported a lot more SWE than any of the other 3 stations, but it does provide a pretty clear evidence of this increase in snow water equivalent right here at the beginning of March. And you can also see it down here in the McClure and North Lost Trail Pass. And the Independence Pass one is kind of hidden under there, but also has a similar increase. So there was an 18% decrease in vegetation at the Conundrum Creek Path compared to only a 2% decrease at the East Snowmass Creek Path as a result of the 2019 avalanches. This coincides with the observations I made from ground truthing. The Conundrum Path was obviously larger and more disruptive to the landscape than the Snowmass Path. Specifically, there was much more soil and rock in the debris field at the Conundrum site, and damage to the flanks was very clear. The trees in the debris field at the Conundrum site were also more beat up than those at the Snowmass Path. Together, these avalanches accounted for 0.7 square kilometers of vegetation loss, and there were more than 1,000 other avalanches that occurred in the same 2 weeks in Colorado. While these 2 were the largest avalanches that happened during the 2019 cycle, the debris from smaller slides is evident throughout Colorado, and especially near Aspen. Avalanche disturbances are responsible for much of the landscape heterogeneity in the Southern Rockies, and they tend to occur more frequently than other disturbances such as wildfire and insect outbreaks. Thus, avalanche paths act as an early successional stage for plant species that are allowed to establish outside of the dense subalpine forests that surround them. This fragmented pattern of vegetation promotes community diversity. The size, growth rate, and age of conifers is a function of avalanche frequency and magnitude, which suggests that avalanches rating high on the R scale and D scale that tend to uproot and relocate massive conifers may essentially expand the habitat of early successional species that persist within the path. In some places, like in the Swiss Alps, there is robust systems for avalanche prevention that exist where human life and establishments are threatened by avalanches. In places where avalanches are prevented, it's been found that stand density, age, and growth rate tend to be greater as the community begins to transition to a later successional stage. This might decrease landscape heterogeneity and biodiversity. So to maintain proper ecosystem function in the high elevation Southern Rockies, avalanches should not be prevented and settlements should instead be located in areas where there is less risk. I also found that snow water equivalent wasn't the only thing that accounted for the return interval of avalanches this large. The return intervals I calculated indicated that similar events would occur every 9 to 21 years, but this doesn't alone account for the occurrence of similar avalanches. Kelly Elder, who is a researcher with the Rocky Mountain Research Station, is currently using dendrochronology to determine the return interval of the 2019 cycle. While the results aren't yet finalized, Elder has identified up to 300-year-old trees that were felled by avalanches in March 2019. This image on the right is someone from Kelly Elder's research team that is collecting tree samples to essentially determine the age of these trees that were in the debris field of some avalanches around Colorado. So the missing piece of this puzzle is the stratigraphy of the snowpack, which ultimately decides when and how big these avalanches will be. In order to better predict avalanches of this size, the weak layers in the snowpack prior to the March 2019 storm could be modeled and considered when similar bulk snow accumulation events occur. Similar recipes of events should carefully be predicted by forecasting agencies like the Colorado Avalanche Information Center to warn the public of potentially catastrophic conditions. This is especially important as recreational backcountry travel becomes more common. So some of the limitations of this, several of them were focused around the nape imagery that I used. One thing that was limiting with this imagery was that it was very temporally coarse. So I could only get images for every 2 years. And as we saw with just sort of the time of year that these images were captured, that also further limited the amount of images I had to work with. So I was working with images that were taken 4 years apart, which was not ideal. The images were also taken in the fall between September and October, which is really late in the growing season, especially for such high elevations. And so probably when some of these images were taken, some of the deciduous vegetation had begun to like winterize or lose its leaves. The nape images are also really large, which made it really hard to store a lot of images. I would have liked to scale this up to a larger area, but I really didn't have the space on my computer since I was working remotely this semester, and I didn't really have the time to do so either. Another consideration is that of the effectiveness of the binary thresholding raster function for the purpose of this spatial analysis. The function doesn't allow a user to input a threshold, although the defined threshold is determined by an algorithm that minimizes intraclass variance. It might have been useful to define my own threshold. Therefore, the results of this function might not be fully representative of the true amount of vegetation that was lost as a result of these avalanches. So the avalanche cycle that occurred in Colorado in 2019 was driven by a relatively stable snowpack that experienced a prolonged snow accumulation event that ultimately led the underlying weak layers to fail, resulting in historic-sized avalanches. I used the NDVI function in ArcGIS Pro to measure the biomass before and after the 2019 avalanches, and then I quantified it using the binary thresholding raster function. I found an 18% decrease in vegetation at the conundrum path and a 2% decrease at the snowmass path, which matched the observations I made when I visited these sites. Although the aftermath of avalanches of this size was really shocking to observe, they truly define the landscape heterogeneity and community diversity that is fundamental to high elevation ecosystems in the Southern Rockies. The trees that were sacrificed by these avalanches will expand the habitat of early successional species. I also calculated the return interval based on snow accumulation events similar to the ones that produced these avalanches, and found that on average, similar events would occur every 21 years. Compared to other ongoing research about this avalanche cycle that dates these avalanches up to 300 years, this return interval does not tell the whole story. However, it's important to explore different methodologies for calculating the return interval because none of them truly tell the whole story. The occurrence of avalanches maintains the community diversity that is fundamental to this ecosystem, even if the avalanches aren't of historic size. When we take humans out of the equation, we can recognize the avalanches as an impressive force of nature that clears the way for early successional plant species to take root. However, humans are increasing their presence in this equation, especially as recreational backcountry use increases every season. For the sake of human life and establishments, it is vital that forecasting centers such as CAKE are able to effectively predict events like this one and to communicate it to the public. Forecasters may consider using some of these methods in conjunction with snowpack modeling to prepare for future avalanche events. So that wraps up my presentation. I'd of course love to thank Stephen for all your mentorship over the years and all of the guidance that you've given me, and it's really shown me kind of where I want to go academically. And of course, your expertise in snow hydrology has been very helpful. Dan, thank you for being available and so helpful with the remote sensing aspects of this project. I definitely could not have done it without you. and Beth for kickstarting my love for maps, starting all the way back at Mountain Campus in watershed class. And thanks for making sure that my maps look nice. All right, I'm gonna stop sharing. I can leave it. Well, I don't know. Do you want me to leave it on the conclusion slide, or should I just stop sharing so we can all see each other?
You can stop sharing, and if someone has questions, you can always go back to that.
Cool.
So we'll open up the floor to questions from general questions from the audience.
Mm-hmm.
So back in the days when we would be in person, there was what's called the Freeman-Smith rule. And at defenses, people would bring some pastries, some coffee, etc. And what we would say when people were not asking questions is, Freeman-Smith rule, if you took a pastry, you have to ask a question. So, Lenka, Kate, Travis, questions?
So was your initial goal to try and see if you could use, like, create a methodology where you could predict, like if somebody in the coming years needed to predict the return was an avalanche, they could use SWE? Was that the general goal?
I think the general goal was kind of to just explore different ways that you could, like different factors that could predict this, like similar events.
Okay.
Because what really defined this avalanche cycle was the like snow accumulation. Like it wasn't like the snowpack was really unstable or anything. It was that so much snow was allowed to accumulate. So we were kind of trying to test how effective snow water equivalent was at modeling or predicting similar events. And yeah, we found that it really wasn't all that great. Like the increases in 2019 were none of them were the maximum increase for all of the data on record. So yeah, there's definitely just like other factors that need to be looked at, but it could be something similar if there was a similar snowpack in the future and they knew that there was this huge storm coming through. That might be another way that they could kind of like look at it.
Okay, so your recommendation would be to maybe maintain really detailed records of what the snowpack looks like, and if there's a storm rolling through, try and compare those layers to what happened in 2019.
Yeah.
Okay, cool. Also, awesome job. Super cool presentation.
Thanks.
Okay, I got a question for you.
Okay.
How do you think that your methodology and sort of what you learned throughout this process could be used in the future, maybe built upon or applied at a bigger scale? Just, you know, now that you really used it on a sort of fine-tuned scale, you looked real in depth at these other avalanches, like, you know, I guess looking forward, how would you maybe use what you've learned here to do another project or learn more?
Yeah, I think that the remote sensing methods, especially where like that we could probably scale that up. And I really would like to do that. There's other researchers that have tried to do similar things and everybody's just kind of used like slightly different methods. So I think it's about kind of fine tuning those methodologies and like coming up with maybe an alternative to the binary thresholding function. But that's something that I'm pretty interested in, and like I would even like to spend more time on is just kind of fine tuning that method and seeing how effective it is at modeling like large scale changes, like kind of like I was talking about, like over an entire mountain range or over the whole state. Like at the beginning of this project, I kind of was looking at it with this like really wide scope. Like I want to find out how much how the extent of vegetation changed over the whole state during this avalanche cycle. But obviously that was, I mean, that's a bit ambitious. But I think that could be something that would be that could be really cool to explore further.
Nice. Excellent job.
Thank you.
Kate, any questions? You don't have to.
That's my mom. She's here for moral support.
That's fine. That's fine. All right. Well, if there are no additional questions, then we'll have the committee then ask Julia some questions, and then when you're done, you can touch base with everyone.
Cool.
So we'll